Welcome back! Today we're going to be running a simple spin-boson model using QClab. We'll assume you have a working installation of QClab already. If you don't, make sure to check out our first video on installing QClab.
The first thing you'll want to do is navigate to the QClab documentation page linked in the description. There, you'll find a page containing each step of this tutorial so you can follow along.
We'll walk through this tutorial in real time thanks to Alex's coding abilities using a Jupyter notebook.
This will enable us to showcase the speed and flexibility of QClab.
Let's get started and first try out using mean field dynamics. First, you'll want to import the necessary external libraries including NumPy and matplotlib. Then, you'll want to import the simulation object, spin-boson model, mean field algorithm, and serial driver. Next, we'll initialize the simulation object, equip it with the spin-boson model and mean field algorithm, and set an initial wave function.
Here, I set the initial quantum population to be entirely in the upper state.
Now, we're all ready to submit the simulation object to the dynamics driver and run our first QClab simulation.
And that's it. I've gone ahead and prepared some visualization code so you can see the result. Here, it's taking us about 8 seconds to run the code, and you can see here is the excited state population dynamics. I'm now going to run all of these trajectories at once by using the multiprocessing parallel driver.
To do that, just import the parallel driver from the dynamics module and rerun the simulation. Parallelizing the code makes it run a lot faster.
As you can see here, the code finished in less than 2 seconds, and the result is exactly the same as expected.
Let's increase the reorganization energy and see the impact on the population dynamics.
To do that, I adjusted the reorganization energy in the constants class of the model object and reran the simulation. You can see how the transient oscillations have been damped out by the stronger coupling to the bath.
Next, let's transition from mean field to using the Fewest-switches surface hopping algorithm instead. To do that, we'll first import the algorithm object and then attach it to the simulation object. We can then run the simulation just like before.
This time, the simulation takes slightly longer because the algorithm is a bit more expensive. It still finishes on my machine in about 6 seconds.
As you may be aware, the original description of Fewest-switches surface hopping incorporated a reversal of momentum when a hop is frustrated. In QClab, the FSSH algorithm is implemented without this reversal, but it is easy to change this behavior as you would like. Simply define a new task and add it to the algorithm recipe. This aligns with how QClab is built, where it's very adjustable to whatever your needs may be.
So here, I'm creating a new task to reverse the momenta of frustrated hops. In the complex classical coordinate formalism implemented in QClab, that just amounts to taking the complex conjugate of those frustrated trajectories. And then I add it to the update recipe of the Fewest-switches surface hopping algorithm and rerun the code. As you can see, the modification doesn't really have a huge impact on the population dynamics.
Let's now change how the spin-boson model couples the quantum and classical degrees of freedom by switching from a diagonal coupling to an off-diagonal one. QClab makes this really easy to do by making a simple coupling Hamiltonian and then vectorizing it using a built-in decorator. After importing the decorator, Alex will define a new ingredient that first gets the classical coordinate and some necessary constants before it uses those constants to construct an off-diagonal coupling matrix. He'll then add this new function to the ingredients list of the spin-boson model and overwrite the existing analytic gradient. This will cause QClab to numerically evaluate the gradient of the new Hamiltonian with a finite difference method.
Now we're ready to run the simulation and see what happens. You'll notice this takes a bit longer than before because we relied on the vectorization decorator in this example. If you make use of NumPy's built-in vectorization, it will run much faster. And there it is.
Huh. Something's a bit fishy. These don't look quite converged, Alex. I see. It's because QClab only does 100 trajectories for 10 units of time by default. While this is helpful to get a sense of how your algorithm works, publication quality data usually needs many thousands of trajectories to be converged.
That would normally take a long time on my laptop. Luckily, I have another Jupyter notebook connected to a high-performance computing node with about 100 CPUs on it. That should speed things up quite substantially. Let me copy over the code and rerun things with more trajectories.
Why don't we adjust the number of trajectories to 20,000 and the total time to 20 units and a time step of 0.005 units.
So now QClab will run 100 processes at the same time. It's going to take about 25 seconds to complete.
So speedy!
Now you can see the resulting data is much more converged.
Now you're ready to explore the rest of QClab's capabilities.
Have fun!